Hi, good afternoon, students. I'm going to finish up this section on equilibrium with this last set of slides, and this will be the last section on the chapter. So let me just go to the very start, and we'll be set to go. All right, this is chapter 13 on chemical equilibrium, and this talk will be much on the last section here. Let me get my color. And that is, we're going to talk about Le Chatelier's principle. First, the definition. Le Chatelier's principle, essentially about any system that is at equilibrium. If you have a system that is at equilibrium and you impose a change, what will happen is that it will readjust. The word here is shift. It will shift in a direction that tends to reduce that change. In other words, it will, the change will disturb the equilibrium, and essentially the system will readjust in order to get back to equilibrium. Now, what does that imply? This principle here helps in the qualitative prediction of the effects of changes due to this. These are the changes that can come about to disturb equilibrium: change in concentration, change in pressure, and change in temperature. So we're going to look at each of these variables as we go on with this lecture. So let's go to the reaction. This is on the formation of ammonia, which is called the Haber process. So nitrogen reacting with hydrogen, all in the gas state. I didn't put the gas state here. All in the gas state, okay, to form ammonia. And the mole ratio is 1:3 to 2. Now, so consider this reaction, and suppose there is an equilibrium described. There is an equilibrium position described by the following concentrations. So we have nitrogen, hydrogen, and ammonia concentration at equilibrium provided. Okay, so then this is disturbed by this. So in other words, you are imposing a change to the equilibrium. Assume that 1 mole per liter, that is 1 molar of N2, is injected into the system. So in other words, with this, you're going to add more of nitrogen. So question is, what will be the result? So predicting the result involves calculating the value of Q. All right, we should know how to calculate the value of Q. Q basically starts with whatever initial concentration that you're given. In this case, you are given the equilibrium concentration, so we can start with that. However, start with this addition of 1 molar. So you have 0.399 and then 1 molar. So the total will be 1.399. That is for nitrogen. For hydrogen remains as is, and ammonia also remains. So with that initial conditions, what we can do is calculate Q. So we evaluate Q. Q, as you know, is the same expression as the K, but now you substitute the initial conditions or concentrations. So here will be 0.202, N2 is 1.399, H2 is 1.197. So you get this. Now, when you get the value of Q, just compare that with the value of K. Now, K can be calculated because we are given the equilibrium concentrations. So this was the concentration at the beginning because the system was set to be at equilibrium. So we substitute in 0.202, 0.399, 1.197. What do we get? 5.96. Now, if you compare these two, 5.96 and 1.70, of course, I'm not saying this because that's both the same exponents. So this is greater than this one. That is, K is greater than Q, or Q is less than Okay, so what does that mean? If Q is less than K, where does the equilibrium shift? It'll shift to the right. That's what we already learned, how to predict the changes based on the value of Q and K. So if Q is less than K, it'll be shifting to the right. So according to this relationship here, adding N2 will shift the equilibrium to the right. And that will result in a new set of equilibrium. So if we allow this to reach equilibrium, it'll come with a new set of equilibrium position. So you can see here, the position in the first is 0.399 of N2, 1.197 of H2, 0.202 of NH3. But now in second position, after you disturb with the addition of nitrogen, 1.348, 1.044, 0.304. So that is essentially what is happening here. So if you disturb an equilibrium, it will adjust to the place where it will reestablish a new equilibrium, but it'll be a different position. It's no longer in the same position as it was before. All right, let's look at another way of looking at this. I'm skipping this slide because it basically talks about the same thing. So another way of saying this principle or statement is that if a component is added to a reaction system, the equilibrium will shift in the direction to lower the concentration of that component. So that's what we have just seen in the previous example. Okay, so now let's move on. Consider this reaction. This is a heterogeneous equilibrium. Heterogeneous, just make sure that you follow me. Heterogeneous meaning more than one phase. Here is a solid, here's a solid, here's a solid, here's a gas and gas. So two different phases. So this is a heterogeneous equilibrium. So if you look at this, arsenic can be extracted from its ore by first reacting the ore with oxygen, that's called roasting, to form solid ASO4, that is arsenic oxide, which is then reduced using carbon. So you can form arsenic by this reduction step. Now, predict the direction of the shift of the equilibrium position in response to each of the following changes. First, addition of carbon monoxide. Second, addition or removal of carbon or tetraarsenic hexoxide. That's the oxide of arsenic. And third, removal of gaseous arsenic. Now, let's look at the first one, addition of carbon monoxide. Now, addition of carbon monoxide, which is a product, will shift away from the substance whose concentration is increased. So in this case, if we look at let's go back to the equilibrium here. So here you're adding carbon monoxide. So it'll shift away from this formation of carbon monoxide. So in other words, it will shift this way. So the first part, equilibrium will shift to the left. Okay, we got that? So that's the addition of carbon monoxide gas. Let's go to the next one, which is addition of pure solid. Pure solid. So how many solids are in this equilibrium? There's two here. So if you add arsenic oxide, this is tetraarsenic hexoxide, and carbon, they are both solids. So if you add either of this, what does it happen? What does it do? So let's go back here. The amount of pure solid has no effect on the equilibrium position. Remember the principle that we learned? Any pure solid or pure liquid does not bring or does not affect the equilibrium. All right, so here is no effect, means no change. Let's go to third one. If gaseous arsenic is removed, what will happen? So let's go back to the equation. Now, this one here, you are removing. You're not adding, you're removing. So if you're removing the arsenic gas, it will adjust to replenish it. So in other words, it'll shift to the right. So let's check the answer there. If arsenic is removed, the equilibrium will shift to the right. Okay, so those are the different changes that can occur and the outcome as a result of the disturbance of equilibrium. So in this way, when you know the direction of change, you can actually exploit that in an industrial sense so that you can maximize the desired product that you want to get. And that's very important for chemical industries. Now let's look at pressure. What will happen when you change pressure in any established equilibrium? Now let's just look at how pressure is changed. There are three ways in which pressure is changed. One is you add or remove a gaseous reactant or product. That'll change the pressure. You add an inert gas, that is one that is not involved in the reaction, and you change the volume of the container. Okay, those are the three ways. Now let's go about looking at this. Addition of inert gas increases the total pressure. When you do that, it does not bring any change to the equilibrium. So in other words, it does not affect the concentrations or partial pressures of reactants and products at equilibrium. Okay, so inert gas, there is no change. What about the next one? When a volume of a container holding a gaseous system is reduced, the system responds to reducing its own volume. So you're reducing the volume, you actually are going to cause a change to that system. The system will want to reduce its volume. So the reduction of volume is the same as increasing pressure. Just know that, because when you decrease the volume, you are going to increase the pressure. So when you do that, it will adjust so that it responds to its reducing its volume. So how does it do that in terms of the reaction? What we'll see is that the total number of gaseous molecules is reduced. So the reason is this: volume is directly proportional to mole. This is from the ideal gas equation. Rearranging the ideal gas equation, we see that volume is directly proportional to moles. So when you change the volume, you're going to change the number of moles. So here, equilibrium position shifts towards the side of the reaction that involves smaller number of gas molecules. So if you reduce the volume, you are going to reduce the mole quantity. Look at this. The same reaction that we've been using from the beginning, that is on the Haber process for the reaction of nitrogen plus hydrogen to give you ammonia. Okay, NH3. Okay, that's the reaction. Let's just balance this up. So the balanced equation is this should be 3, and that is 2, and that should take care of the equation. So if you look at this equation here, a mixture of ammonia, nitrogen at equilibrium, the volume is suddenly decreased. So in other words, you decrease the volume by pushing that on that piston, and you reduce the volume. Look what happens. You are increasing the pressure also in here. But when you reduce the volume, guess what will happen? You see here a lot of the molecules are evenly distributed. You see hydrogen, you see nitrogen in here. Now you see here, there is some ammonia forming, but not to a great extent. But look at this one. You see ammonia is really getting more and more. A lot of ammonia. So what happens when you are increasing the pressure or reducing the volume? When you reduce the volume, it favors the area or the side that has lesser number of moles. So how many moles of gas on this side? That'll be 1 plus 3 equals 4. There are altogether 4 moles of gas from the stoichiometry. How many moles of gas on the right-hand side? 2. So which side will be favored when you reduce the volume? The less number of moles. So that basically is the argument in there. So let's look at the direction of change to this one. Again, another heterogeneous. Can you see that? There is solid, gas, and liquid. So assume that the volume in this case is reduced. So where will the equilibrium shift? Now you look at the gaseous product. That is what is going to be critical when you're looking at volume reduction. So this is the only gaseous product. And if you're going to reduce the volume, which side will it favor? So the number of gas molecules here, or moles, is 6. On the product side, 0. There is no gas. So where will the equilibrium shift if you reduce the volume? To the right. So since P4 and Cl are pure solids and pure liquid respectively, we do not need to consider only the effect. We need to consider only the effect of change in the volume of Cl2. All right. So volume is decreased, so the position of the equilibrium will shift to the right. Okay. Now let's look at this last part here, temperature. How does the temperature? We know that temperature is related to K. You change the temperature, you change the value of K. So now let's consider the synthesis of ammonia once again. So nitrogen, hydrogen, ammonia. And thermochemically, this is the equation. Ammonia is produced with this amount of heat that is given off. Notice that this is not written in the proper thermochemical sense. In a proper thermochemical sense, we will write it delta H is equal to minus 92 kilojoules. That's the proper thermochemical sense. Why? Because it is an exothermic reaction. It's an exothermic reaction. But when we are discussing it in terms of Le Chatelier's principle, this is what we do. If we have an exothermic, we put the energy as a product. Let me repeat that again. If you're writing it in the Le Chatelier's equilibrium form, if it's an exothermic, we put the energy as a product, like what is shown here. And vice versa. When we look at an endothermic, we'll put the energy as a reactant. So we'll look at that later. So let's look at this one. According to Le Chatelier's principle, the shift will be in the direction that consumes energy. So consider the synthesis of this, and concentration of ammonia decreases, and that of N2 and A2 increases, thus decreasing the value of K. So here, what happens when you increase the temperature? If you increase the temperature, it will shift to the direction where there will be less energy that is favored. So in other words, you see here, it is part of the product. So if you increase the temperature, which is increasing energy on this part, it will shift to the left. And to the left means you will increase the concentration of N2 and H2. Now let's look at the decomposition of calcium carbonate, and this forms that. In the thermochemical equation, delta H will be equal to plus 556 kilojoules. Notice that if we write it in the proper thermochemical form, delta H is equal to this, which is endothermic. Okay, endothermic. That's endothermic. So when we are writing it in an equilibrium using the Chatelier principle, we put it as a reactant. All right, let's see. If we increase the temperature, guess what will happen? So you increase temperature, you increase this energy. It is a reactant. So if you are increasing this side, that means it will move there. It will shift the equilibrium to the right. So this is one thing about temperature. So in the temperature, if it's endothermic, the energy is on the left, that is the reactant side. If it's exothermic, the energy is on the product side. And if you increase, you use the same argument as you have done in increasing the species on the right or left. The change will occur in the same way. So treat energy as a reactant for endothermic, and or a product for exothermic. And then you can predict the direction of the shift in this way. Okay, let's look at this one here. For the following reaction, predict how the value of K changes as temperature is increased. So here you see, I've written this in the thermochemical sense. So you should know here that this is exothermic. So if it's exothermic, this will be plus 198 kilojoules in the product. So if you increase the temperature, you are increasing this energy here on this side, the right-hand side or the product side. So your reaction must go to the left. So that would be the direction of change in the equilibrium. So this is an exothermic reaction. Energy can be regarded as a product. As the temperature is increased, the value of K decreases. The equilibrium shifts to the left. All right, so let me just finish off with this one here. So here you will see that at 100 degrees centigrade or Celsius, you see here that you have more of the NO2, okay, whereas at 0 degrees Celsius at freezing, N2O4. So basically what it says in here, that equilibrium is essentially very much temperature influence. So temperature is very important, and you can see the big contrast in the changes as you freeze this or as you bring it to a higher temperature. And these are the changes. I'll just go through one and you can go through the rest of that. Say, for example, if you disturb the equilibrium by adding N2O2 gas, okay? If we go back, if you add N2O2, let me see, add NO2 gas. So you're going to add this. So if you add that, let me just remove this pen. So let me go back. Let me go back. So if you remove this, that means, oh, sorry, I missed that. If you're going to add NO2, it will shift to the left. What about if you add inert gas? Inert gas that wouldn't react with any of the reacted dot products. What will be the change? None. What about if you increase the volume of the container? Okay, increase the volume of the container. Let's go back here. Here, increase the volume of the container. Which one will be favored? So here you look at the moles. Here is 1 mole of gas here on the left. Here is 2 moles of gas on the right. Let me write the 2 here. 2. So if you increase the volume, so it says here, increase the volume. If you increase the volume, which side it will favor? Volume means you are increasing the number of moles of gas, so it'll favor to the right. There is 2 here, and there is only 1 there. So that's what the answer is, to the right. Okay. Suppose we have the following reaction at equilibrium: calcium carbonate, solid, calcium oxide, solid, and carbon dioxide gas. What happens to the equilibrium when the additional calcium carbonate is added to the system? Now look at calcium carbonate. It is a solid. If you add more of a solid does not affect equilibrium. So this is the choice. There will be no change in the equilibrium. So here, addition of solid will not change equilibrium. That means if you add or remove this, and if you add or remove this, there will be no change. All right, that brings an end to this set of video. I hope you'll be able to follow through and read through the rest of the notes. Thank you.